This video describes what's inside a battery and how it is that batteries go about generating electricity. This picture shows a very simple schematic of what a simple battery might look like on the inside. A battery is made up of two chambers called half cells, and in the picture shown, one half cell is made up of a solid piece of copper and a copper sulfate solution. And then the other half cell is made up of a solid piece of zinc inside a zinc sulfate solution. And there is a wire connecting the two pieces of metal. And additionally, there is this thing called a salt bridge. Taking a closer look at what we call the copper half cell, the copper half cell is made up of two parts. First of all, there is a solid piece of copper. And that solid piece of copper is made up of copper atoms, which are not charged. So a pure substance, a pure element, has no charge, so its oxidation state is 0. So all of that copper atoms in the solid piece of copper have a charge of 0. And then there's also a beaker of copper 2 sulfate in which that solid piece of copper is submerged. And the copper 2 sulfate, because it's been dissolved in water, has dissociated. So the copper sulfate solution is actually a mixture of two different substances. There are copper ions with a charge of 2+, and there are sulfate ions with a charge of 2-, mixed together within that solution. On the other side, we have the zinc half cell, and the zinc half cell looks very much like the copper half cell. We have a solid piece of zinc, metal, and all of the atoms in the solid piece of zinc have a charge of 0. And then we have a beaker of zinc sulfate, and again, because it's been dissolved, the zinc sulfate's been dissolved in water, the zinc and the sulfate have dissociated from one another, and so there will be zinc ions floating around in the solution with a charge of +2. And separate from the zinc ions will be a sulfate ions floating around in there with a charge of -2. When we connect the solid piece of zinc to the solid piece of copper with a metal wire, electrons begin to flow from the piece of zinc, so out of the piece of zinc, into the piece of copper. And we know that electron flow is what causes electrical current. So electrical current is the result of electron flow. So we're creating electrical current when electrons begin to move from the zinc over to the copper. And the question is, how do we know, or why is it that the electrons move from the zinc over to the copper rather than the other way around, so from the copper over to the zinc? And the answer to that question has to do with the electrical potential, or the ease of oxidation of the two metals. This chart was copied from the IB data booklet and shows standard electrode potentials of a whole bunch of different substances, primarily metals. And the thing about this chart is that it's arranged such that the most easily oxidized metals are on the top of the chart. So lithium would be the most easily oxidized metal. And at the bottom of the chart, there are the least easily oxidized metals. And so if we remember that oxidation is referring to losing electrons, lithium, because it's at the top of the potential chart, loses electrons more easily than the other metals on the chart. We can use this list of standard electrode potentials as an activity series to predict the products of single replacement reactions, but we can also use it to tell us which way electrons will flow if two metals are connected by a wire. So in this case, in the example we've been talking about, we have zinc and we have copper, and I've circled in red here the locations of zinc and copper on this electrode potential series. And I see that zinc is higher up than copper on the potential series, which means that zinc is more readily oxidized or loses electrons more easily than copper. And this is why, if I connect zinc and copper to each other, the zinc will lose electrons to the copper. So again, to reiterate, the electrons are flowing out of the zinc into the copper, and we can tell that because zinc is higher on the potential series. It's more easily oxidized than the copper. All right, now let's look at what goes on in the zinc half cell when the zinc bar starts losing electrons. So we pointed out earlier that before we connected the wire, the zinc atoms in the solid zinc bar had a charge of 0. As they lose electrons, each zinc atom loses 2 electrons and becomes charged. It has a charge of positive 2. And the thing about becoming charged is that when the zinc becomes charged, it also becomes water soluble. So zinc that has a charge of 0 is not water soluble. Most, or I guess all metals, when they are uncharged, are not water soluble. I can take a piece of copper, I can take a coin, I can drop it into water and it's not going to dissolve. So pure metals with charges of 0 don't dissolve in water. But metals that are charged are water soluble. So as these zinc atoms become charged, they begin to dissolve into the zinc sulfate solution. So I have little zinc atoms in the zinc bar going into this zinc solution, the zinc sulfate solution. Because of that, the zinc bar is going to get smaller in size over time. And also because of that, this concentration of zinc atoms or zinc ions in the zinc sulfate solution goes up. So I can draw a little up arrow here. The concentration of zinc ions in that solution increases as time goes on. Because the zinc is losing electrons, we say that oxidation is occurring at the zinc half cell. And the half cell where oxidation occurs we refer to as the anode or the negative electrode. So those are vocabulary words that you'll want to know. The anode and the negative electrode are the same thing, and they are the side of the battery where oxidation occurs, where electrons are lost. All right, now let's look at what goes on in the copper half cell. So we have these electrons and they're traveling across this wire, and they get to the solid piece of copper, and the solid piece of copper isn't going to accept those electrons. The atoms in the solid piece of copper already have a charge of 0, and if they were to accept more electrons, they would become negatively charged. And metal atoms don't really become negatively charged. So the electrons can actually pass through this solid piece of copper, and then you can imagine them sort of collecting at the end of the solid piece of copper. And the thing about electrons is that they're negatively charged. And the thing about the copper sulfate solution, this blue solution, is that it contains copper ions that are positively charged. And we know that opposites attract, so the negative electrons and the positive copper ions are attracted to one another, and copper ions begin to migrate over to the solid copper bar where those electrons are coming through. As they come over, the copper ions get reduced, meaning that they gain electrons. So we start out with copper with a positive 2 charge. When the copper ions get to the copper bar, they can pick up 2 electrons and become copper with no charge, so neutral copper. Again, copper ions can dissolve in water. Copper that's neutral cannot dissolve in water. And so these ions that were in solution begin coming out of solution, and they essentially precipitate onto the surface of that solid copper bar. And so the solid copper bar is going to get bigger over time, and also the concentration of the copper ions in the solution is going to go down over time because the copper ions are going to, in fact, collect on the bar. The electrode where this happens is called the positive electrode or the cathode, and that's the half cell where reduction occurs. The last piece of the voltaic cell that we need to talk about is the salt bridge and its purpose and its function. The purpose of the salt bridge is essentially to get electrons back where they started. So hopefully we remember that electricity only flows in complete circuits. So the electrons have to be able to get back where they started from. And what we've talked about so far is that the electrons come out of the zinc and they go over to the copper, and then they get stuck because copper atoms come and migrate and essentially bond with the electrons. That's not the right word. But the electrons that come out of the zinc become a part of copper atoms, and then that sort of stops the flow of electrons. And in order for us to conduct electricity, conduct electrical current, electrons have to be able to get back where they started. And the purpose of the salt bridge is to transfer electrons from the copper sulfate solution back over to the other side where they came from originally, since they originally came from the piece of zinc. A salt bridge is really anything that is porous and will soak up water. So in high school chemistry labs, salt bridges typically are things like paper towels or maybe shoestrings or a lab apron string. Pretty much anything that's porous can be used as a salt bridge. And the salt bridge is soaked in some sort of salt solution. The salt solution is also often potassium nitrate dissolved in water, but it doesn't have to be. The reason that the salt bridge exists is to get negative ions over the salt bridge in whichever direction completes the electrical circuit, because the negative ions, remember, are holding on to extra electrons. Nitrate, for instance, has a charge of -1, so it's got one extra electron compared to its proton count. And so we can shuttle electrons over to the other side if nitrate ions move from one side of the battery to the other. So it's not the same electrons that came from the zinc, but it's the same total number of electrons, even though that they are different electrons that are traveling over to the other side. So nitrate ions flow over the salt bridge. In this case, they flow over the salt bridge from right to left, so this way, because that's the direction that completes the electrical circuit. So the entire circuit goes, we start out at zinc, then we go across the wire over to the copper, and then we have new ions coming from the salt bridge and over to the other side. The last thing that you need to know about what's inside a battery is how to calculate the voltage that two particular half cells will generate. And it's very easy to do that. All you have to do is look at the standard electrode potential off of the potential series for the two metals of interest to you, and then you use the simple equation that the voltage or the electrical potential, which we abbreviate with E here, the electrical potential of the cell is equal to the potential of the cathode minus the potential of the anode. So going back to our potential series, again, we can see that copper, that was our cathode, and if we look here, we can see that copper has a potential of positive 0.34. Zinc, on the other hand, which was our anode, has an electrical potential of negative 0.76. And to get the overall electrical potential of the battery, we take the potential of the cathode minus the potential of the anode, and this particular battery has a voltage of 1.1 volts. The last thing I would like to say about Voltaic cells is that we refer to the flow of electrons in this situation as spontaneous. Notice we didn't have to do anything to force the electrons to flow in the direction that they did. They did it naturally when we connected all of the pieces in the right order. This stands in contrast to something called an electrolytic cell. And electrolytic cells, the electron flow is forced in the opposite direction from normal. But in a voltaic cell, which produces electricity, electron flow is what we call spontaneous or non-forced.